This lesson is about systems of inequalities. And what we're going to learn about are inequalities that involve two variables. The solutions to these inequalities must be graphed on a two-dimensional plane, similar to how when we had inequalities involving a single variable, we would graph on the real number line. So for instance, given an inequality such as y is greater than or equal to 3/2 x minus 3, a solution to the inequality is an ordered pair xy that makes this statement true. For example, 2, 3. My x-coordinate in this point is 2, and my y-coordinate is 3, so when I plug this into my inequality, I have 3 is greater than or equal to 3/2 times 2 minus 3, or 3 is greater than or equal to, these 2's will cancel each other out, leaving me with 3 minus 3, or 3 is greater than or equal to 0, which is a true statement. So therefore, the point 2, 3 is a solution to this inequality. However, there are many others as well, and there's no very good way of expressing the solution to these algebraically. So we rely on graphing the solution to an inequality. The graph of an inequality is the collection of all solutions to the inequality. Since there are so many possibilities for answers, this is considered the most efficient way to display the solution. To graph an inequality, you start by sketching the curve as you would normally, except that if you have greater than or less than symbols in your inequality, you're going to graph the curve using a dashed line. If you have greater than or equal to or less than or equal to, you're going to graph using a solid line. Next, the plane will be parted into two separate regions. In each region, one of the following statements will be true. All points in the region are solutions, or none of the points in the region are solutions. To determine which region is the solution region, we pick a test value, usually 0, 0 if it's available. If the test value results in a true statement, then we shade the part of the plane that contains the test value. If it results in a false statement, then we shade the part of the plane that does not contain the test value. So let's graph the solution to y is greater than or equal to 3/2 x minus 3. The first thing that I'm going to do is graph it as if it were an equation, but in this case I will use a solid line because it's y is greater than or equal to. So the y-intercept is -3, so that's located right there, and I have a slope of 3/2. So if I go up 3 and over 2, that's going to give me another point on my line. Up 3 and over 2, there's another point, and I'll go one more just so I get a nice accurate graph. Or I could go down 3 and back 2. That'll work as well. But once I have enough points that I'm comfortable I could draw an accurate graph, I'll go ahead and sketch that in. And again, I'm using a solid line because it's y is greater than or equal to. So what's happening here is either, the plane is parted into two regions. So I'll call this region 1, which is everything basically above my line, or region 2, which is basically everything below my line. One of these two regions is the solution region, meaning that every single point, if I plug in every single point in that region, it would result in a true statement. So we just have to test one point. And the easiest point to test is the origin. The only time that we couldn't test the origin is if our graph passed through the origin. Since that's not the case here, we're free to use that. So when I test the origin, my x value is 0 and my y value is 0. So when I plug this in, my inequality becomes 0 is greater than or equal to 3 halves times 0 minus 3. Or 0 is greater than or equal to negative 3. This is a true statement. Since that's a true statement, then the side of the line that contains the origin is the solution region. So here's the origin. The side of the line that contains the origin is the solution region. So what that means is this side of the line, every single point over here are solutions to my inequality. So that graph represents the collection of all solutions to my inequality. And if I chose a point in the other region, so I'm going to choose a random point. This is the point with coordinates 5, 2. If I use that as a test in my inequality, what I'm going to learn is that is not a solution, because every single point in region 2 is not a solution to my inequality. So to show you that, 5, 2, if I plug that in, I would have 2 is greater than or equal to 3 halves times 5 minus 3. Or 2 is greater than or equal to 15 halves. And in order to combine, I need to get a common denominator. So I need 3 with a denominator of 2. So that's going to be 6 halves. Or 2 is greater than or equal to 15 minus 6 is 9. 9 halves. And 9 halves, if you change that into a decimal for comparison, that's 4.5. 2 is definitely not greater than 4.5. That is a false statement. Any point that I chose in region 2 would lead to a false statement for my inequality. Any point that I choose from region 1 would lead to a true statement to my inequality. So this graph represents all the solutions to my inequality. What we're interested in this section are systems of inequalities. In order to solve a system of inequalities, I need to first graph all inequalities in the system on the same set of axes. Then the region where all shaded regions overlap is the solution to the system. So for example, I want to solve the system x plus y is greater than 6 and 2x minus y is less than or equal to 0. In order to solve this, what I need to do is graph each inequality separately, but on the same set of axes. I'm going to do so using 2 different colors so that you can really see the overlapped region. Although when you're doing your homework, generally you're using a pencil, and it's rather difficult to do that. So you'll need to come up with some method for yourself so that you can identify what the solution region is. So I'm going to use blue for my first inequality, and I'll use green for the other one. So x plus y is greater than 6. In order to graph this, it's going to be easier to do so if I write it as y is greater than negative x plus 6. And similarly, getting y by itself in the other equation is going to be helpful. I would have negative y is less than or equal to negative 2x, but I need to divide both sides by negative 1. But just remember, when you divide both sides by negative 1, you flip your inequality. Okay, let's start with the first line. Y is greater than negative x plus 6. So I have a y-intercept of positive 6 and a slope of negative 1. Meaning to get to the next point, I would go down 1 and over 1, down 1, over 1. And similarly, until I have enough points that I feel confident that I can get an accurate sketch of the line. I'm going to do quite a few here because I think I need a good, accurate sketch. What I need to be careful of is it's very tempting to want to draw this line in using a solid line. I need to draw this in using a dashed line. The reason it needs to be a dashed line is because I only have a greater than symbol in this inequality, not greater than or equal to. So I'll do just that. I'll draw it in with a dashed line. Now I need to choose which side of the line is going to be a solution region and which side is not a solution region. And I'm only going to shade the solution region. So y is greater than or equal to negative x plus 6. It does not pass through the origin, so I can test the origin 0, 0, which means when I plug this in, I would have 0 is greater than negative 0 plus 6, or just 0 is greater than 6. Well, that is false. And since that's false, I would shade the line, shade the side of the line that does not contain the origin. So I would shade this side of the line over here. Okay. Now I'm going to work on my other line. So y is greater than or equal to 2x. This is a line that passes through the origin and has a slope of 2. So I would go up 2 and over 1, up 2 over 1, up 2 over 1, up 2 over 1. And I'll do one more that way, or I could go down 2 and back 1 to get some additional points this direction, just to make sure I have a nice accurate depiction of my line. And this line is going to be drawn in with a solid line. So, because it's a greater than or equal to, so I'll sketch it in with a solid line. And now I just need to decide which side of the line is going to be shaded. Well, to decide which side of the line is going to be shaded, I cannot use the origin because my line passes through the origin. But I can use any point that's visibly on one side of the line or the other. So I'm just going to pick a point at random. This point has the coordinates 2, 0. So that's what I'm going to use as my test value. So this would be 0 is greater than or equal to 2 times 2, or 0 is greater than or equal to 4, and that is false. Which means I just need to shade the side of the line that does not contain that point. So I'm going to shade this side of the line over here. And one thing that I noticed students wanting to do is to use the axes as boundaries as well, but the axes are not the boundaries for when you should stop shading. It's going to be just one side of the entire plane or the other. It has nothing to do with stopping or starting at any of the axes. Now, the overlapped region, in the solution region, is the region where all regions overlap. So in this case, this little triangle up here at the top, that is my solution region. And it's best to be able to describe it graphically because of the points where you have intersections are visible, the boundaries, some are solid, some are dashed. It makes it very visible what your solution is. I've also graphed this a little bit nicer down here where you can see it that right there, in case you can't interpret my picture all that well, this is a nice depiction of what the solution region in this example would look like. So your final answer doesn't have to look as nice as this, obviously, but it does need to very visibly demonstrate which region is your solution region. And sometimes when you're using pencil, you do have, a lot of, makes it difficult to decide which is your solution region or not. So just make sure you indicate to your instructor on a test which one it really is. Something like that would be sufficient. Let's take a look at this next system. So I have x squared minus y is less than or equal to 3, and x plus 2y is less than 2. Now, I'm going to graph both of them on the same set of axes. The first one is not linear, but it's more of a parabola. First thing I'm going to do is solve it for y. So I would have negative y is less than or equal to negative x squared plus 3 if I move my x squared term to the other side by subtraction. Then if I divide both sides by a negative, I have y is greater than or equal to x squared minus 3. For this, when I graph, I'm going to have a parabola, and it's shifted down 3 units, and it has points here and here, and I'm not going to be terribly accurate with the rest of it. I'm just going to sketch in a parabola. That works just fine. Okay, next, oh, and I did use a solid line to graph my parabola because of the greater than or equal to. The next curve, I'm going to solve this for y. So 2y is less than negative x plus 2, or y is less than negative 1/2 x plus 1. So this is a line, and when I graph this line, the y-intercept is positive 1, and I have a slope of negative 1/2. So if I go down 1 over 2, down 1 over 2, and so forth, or up 1, back 2, up 1, back 2, then that's going to give me an idea of the direction of my line pretty good. I need to draw this in with a dashed line. And there we have that. Okay, so I am not omitting the part where I draw in my shade in my solution regions. I'm purposefully waiting for the end so that I don't have to go about shading too much. So here's what I'm going to do. I'm going to start with my parabola. So I'll go back to blue here. And my parabola does not pass through the origin. So I'm going to be able to test the point 0, 0 for that equation. When I plug this into y is greater than or equal to x squared minus 3, I would have 0 is greater than or equal to negative 3. 0 is larger than negative 3, so this is a true statement, which means I shade the side of the parabola that contains the origin. So I'm going to wait before I do that, though, so that I don't have to shade too much. All right, but I know what side of my parabola I'm going to shade. And then the line, again, the line isn't passing through the origin either. So I'm going to test the origin with the line. So 0 is less than 1 when I plug into my line equation. 0 is less than 1, so that's a true statement. So the side of the line that contains the origin. So the side of the parabola that contains the origin is like this side right here. The inside of the parabola, if you if you will. The side of the line that contains the origin is this side here. But I'm not going to shade the entire plane, because technically I would need to shade the entire plane, but in order to visibly see the solution region a lot better, I'm going to skip shading the entire lower side of the xy plane here. So the solution to the system is right here. This is my solution region. And so you can see it better. I've graphed it a little bit nicer, and it looks like this.
In this next example, we have a set of inequalities. The first function is, or first equation is, x squared plus y squared is less than or equal to 36, and the second is x plus y is less than 4. The first function, let's work with it. So we have x squared plus y squared is less than or equal to 36. If I set that equal to 36, it might be more recognizable as to what type of shape that's going to produce. This should be recognizable as a circle of radius 6. So if I come over here on my chart, I would want to draw, as best I can, a circle of radius 6. So I'm just going to mark a few points where I have a radius of 6, and then draw in the best circle that I can here. All right, now I used a solid line because this was less than or equal to 36, and so I would use a solid line there, not a dashed line. But the next thing that I need to do is shade, and I'm either going to shade on the inside of the circle or on the outside of the circle. And with circles, it's actually pretty easy to determine. If these are the points on the circle, if we want them all to be less than 36, that's the boundary. So that means we're going to shade the inside of the circle. But you can still do a test. So if you take the test point 0, 0, for instance, and you plug that into your equation, you would have 0 squared plus 0 squared is less than or equal to 36. So that means 0 is less than or equal to 36, which is true. So we would shade the inside of the circle. So this inside portion is shaded. Next, the other curve here is a line, and it's based off of x plus y is less than 4. For the time being, I'm just going to set that equal to 4 to draw my line. Now, it would be easier to sketch if I had it written in y equals mx plus b form. So if I just move that x term over, so negative x plus 4. Now, I am going to make sure I use the dashed line because this is less than 4. So let's see here. I'm going. There's positive 4 on my axis. There's positive 4 there. And so I have a slope of negative 1, so going along right through here. That is my line y equals, or x plus y is less than 4. Now, I do need to determine which side of the line I need to shade. And it's a little less obvious as to just determining always which side you're supposed to shade. But you can always use a test value, and the test values are generally very easy to do. We'll just use the point 0, 0, plug it into the function. So we have 0 plus 0 is less than 4. And that is a true statement. So what that means is I would shade the side of the line that contains the origin, which would be this side of the line over here. All right, now, the last thing is, what part of this is the solution region? So the solution region, I'll switch over and use a different color here. The solution region is going to be the part that is contained for the overlap region. So right along here and along this dashed line and everything on the inside of that. That is the solution region for this particular inequality or set of inequalities. And if you want to see a better picture than what I've drawn, I actually made one here, although the inside part that got shaded didn't quite show up so well. But all of that on the inside there is shaded in green because it is part of the solution region.